Two bags of white powder sit in different places. One is in a farmer's barn. The other is in a bombed-out warehouse. They are the exact same substance, and that is the whole story. Right now, half the nitrogen atoms inside your body were not made by nature. They were manufactured inside an industrial reactor. Without this powder, roughly 4 billion people alive today would simply not exist. The food that fed them could never have been grown. We are, in a very literal sense, made of industrial chemistry. Our bodies are built from a factory process invented just over a century ago. But this same powder has also blown up ships, leveled cities, and fueled wars that killed millions. The same molecule, the same white crystals. The man who invented the process to make it won the Nobel Prize. He also supervised the first large-scale use of chemical weapons in history. His wife begged him to stop. A brilliant chemist herself, she called what he was doing a perversion of science. Weeks later, she was dead. This is the story of one molecule that saved civilization and cursed it at the same time. A discovery that contains the whole contradiction of human progress. So how did one white powder come to run the world? It starts with a problem that nearly ended humanity before the 20th century even began. The year is 1898. Across Europe and America, cities are swelling faster than anyone thought possible. 1 billion people already walked the earth, and that number was climbing every decade with no sign of slowing down. But the land that fed all those people was quietly dying. Centuries of farming had stripped the soil of the one thing crops desperately need: nitrogen. Nitrogen is the engine of plant growth. Without it, roots struggle, leaves yellow, and harvests collapse to almost nothing. For centuries, farmers had one solution: manure. Spread enough of it, and the soil recovered. But manure could not keep pace with 1 billion hungry mouths. Then came guano. The droppings of seabirds packed centuries deep on remote Pacific islands turned out to be extraordinarily rich in nitrogen. Ships hauled it halfway around the world to European farms. For a few decades it worked. Then the islands ran out. So the world turned to Chilean saltpeter, massive mineral deposits in the Atacama Desert. It was a nitrogen bonanza, but a finite one. In 1898, the British scientist William Crookes stood before the world and delivered a stark warning. Within a generation, the deposits would be gone, and billions would starve. The cruel irony was that nitrogen was everywhere. It makes up 78% of every breath you take. But in the air, it is locked in pairs, chemically inert, completely useless to any plant. Someone had to find a way to break that lock, to crack open the nitrogen molecule and make it useful. That someone was Fritz Haber. Fritz Haber was a short, bald, intensely driven chemist working in Karlsruhe, Germany, around 1904. He wore pince-nez glasses and burned with patriotic ambition. He was Jewish in a country that barely tolerated him. So he channeled everything into science, into being more German than the Germans, into solving the unsolvable. The problem he attacked was this: nitrogen gas floats everywhere in the air, but the two nitrogen atoms cling to each other with one of the strongest bonds in all of chemistry. To make ammonia, Haber needed to force nitrogen atoms apart and bond them with hydrogen. Nature almost never does this. Lightning manages it occasionally. That is about it. Haber's lab became an obsessive battlefield. He tried catalyst after catalyst, hundreds of them, searching for the chemical key that would force this reaction to happen. He discovered that with extreme heat, around 500 degrees Celsius, and crushing pressure, around 200 atmospheres, and an iron catalyst, the reaction would actually work. On the 2nd of July 1909, Haber's small tabletop apparatus dripped liquid ammonia for the first time. Drop by tiny drop. It worked. He had done what billions of years of evolution had barely managed. He had pulled nitrogen from the air and turned it into something a plant could actually eat. Historians would later call it one of the most important chemical reactions ever discovered. Some say it is the single invention that allowed the modern human population to exist. Haber licensed his process to a massive German chemical company called BASF, and that decision would change the world in ways no one could yet imagine. BASF didn't just buy a patent. They handed it to one man and said, "Make this work at scale." That man was Karl Bosch. Tall, broad-shouldered, with a mind that moved between chemistry and engineering, like most people move between rooms. Haber's lab process worked beautifully at small scale, but small scale feeds no one. Bosch had to think in tons, not test tubes. The problem was brutal. High-pressure hydrogen gas at extreme heat destroys steel from the inside. The first reactor tubes kept exploding. Bosch ran experiment after experiment. 4 years, 20,000 attempts. He was not a man who quit. His breakthrough was lining the steel tubes with soft iron. The iron took the hydrogen's assault. The outer steel held the pressure. Problem solved. In 1913, the Opal plant opened in Germany, the first facility of its kind anywhere on Earth. It was enormous. The plant converted ammonia into ammonium nitrate fertilizer. And then something remarkable happened. Crop yields across Germany began to climb. Fields that had struggled for decades suddenly produced harvests no one had seen before. The nitrogen gap that had haunted agriculture for centuries was closing. People called Bosch the originator of fertilizer production, the man who turned air into bread. It was not an exaggeration. But the same factory that fed the world was about to be turned toward something far darker. In August 1914, Germany went to war. And within months, the Opal plant was quietly converted to produce military explosives. Britain's Royal Navy had blockaded Germany's ports, cutting off the supply of Chilean saltpeter. Without it, Germany had no nitrates. Without nitrates, no gunpowder. Military analysts estimated Germany would exhaust its munitions reserves within 6 months. The war would end not by victory, but by running out of bullets. Haber-Bosch changed that calculation entirely. Synthetic nitrogen from air meant Germany could manufacture explosives indefinitely, blockade or not. Historians have argued ever since that Haber-Bosch extended the First World War by 2, perhaps 4 years. Millions of lives prolonged by a chemistry experiment. Fritz Haber did not see a contradiction. He believed serving Germany in war was the same as serving science in peace. He threw himself into the war effort completely. He proposed a new kind of weapon. Not bullets, not shells. Something that would drift silently across the battlefield and could not be outrun. Chlorine gas. The 22nd of April 1915. The town of Ypres, Belgium. Fritz Haber stood on a ridge and personally supervised the release. 168 tons of chlorine drifted toward French and Algerian troops. Soldiers described a green-yellow wall moving toward them. Then the burning began. Over 5,000 men died. Haber returned home a celebrated hero. His wife, Clara, the first woman to earn a chemistry doctorate in Germany, was waiting for him. Clara Immerwahr was not the kind of woman Germany knew what to do with. She had fought for a decade just to be allowed to sit the doctoral exam. In 1900, she became the first woman to earn a chemistry doctorate from the University of Breslau. The degree cost her everything except her mind. She married Fritz Haber the same year. She believed in science as a force for human good. He believed in science as a force, full stop. When the war began and Haber turned the lab toward poison gas, Clara did not stay silent. She called it a perversion of the ideals of science. He dismissed her. The gas attack at Ypres went ahead, and on the night of the 1st of May 1915, Fritz Haber came home from the front. He had just been promoted to captain. His colleagues toasted him. The evening was full of celebration inside those walls. Clara was there, watching. At some point in the night, she walked out into the garden alone. She took his service revolver with her. A single shot rang out in the early hours. Their 12-year-old son, Hermann, found her. She died before morning came. The next morning, Fritz Haber packed his bags and left for the Eastern Front. The work, he had decided, could not wait. The war ended in November 1918. The guns fell silent, the trenches emptied, and Europe began the long work of counting its dead. But the factories did not stop. Dozens of enormous ammonia plants across Germany kept their furnaces burning, their pressure vessels humming. They had no war left to feed. The German chemical industry made a decision. The same nitrogen that had filled artillery shells would now fill bags of fertilizer. The machines barely needed adjustment. Farmers who had watched their soil exhaust itself during the war years suddenly had access to cheap synthetic nitrogen on a scale nobody had ever imagined. Then came the Second World War, and the whole terrible cycle repeated. By 1945, the United States alone had built enough ammonium nitrate capacity to blow apart continents. When peace came, the U.S. government looked at its mountains of leftover ammonium nitrate and made a remarkably simple choice. They gave it to farmers. Crop yields responded immediately. American corn harvests doubled, then doubled again. Fields that once fed a family now fed a town. Through the 1950s, 60s, and 70s, the Green Revolution swept the world. New crop varieties bred to drink up synthetic nitrogen produced harvests that previous generations would have called miraculous. In 1950, the world held 2.6 billion people. By the year 2000, it held more than 6 billion. The curve of population growth tracked almost perfectly with the curve of nitrogen fertilizer output. But the same molecule that was feeding the world carried a darker nature. Ammonium nitrate is an oxidizer, and under the wrong conditions, it does not burn. It detonates. The first catastrophic warning came in 1921 at the BASF plant in Oppau, Germany. Workers needed to break up a massive hardened silo of fertilizer. They used dynamite. They had done it hundreds of times before with no problem. On September 21, something was different. The charge hit the wrong mixture, and the entire silo disappeared. More than 500 people were killed. The crater left behind was 30 meters deep. An entire neighborhood of Oppau simply ceased to exist. The world took note, issued warnings, updated safety guidelines, and then, as the decades passed, it gradually forgot. Until the 16th of April, 1947, in a port city called Texas City, Texas. The SS Grand Camp sat in the harbor loaded with 2,300 tons of ammonium nitrate, bagged and bound for Europe. Somewhere in the hold, a small fire started. The crew tried to smother it. Instead of flooding the hold with water, they sealed the hatches and tried to steam smother the fire. That decision trapped heat. The temperature inside climbed toward a threshold no one wanted to reach. Hundreds of spectators and firefighters had gathered on the dock to watch the smoke. At 9:12 inches the morning, the Grand Camp simply vanished. In a single instant, the blast wave traveled outward at the speed of sound. Windows shattered in Houston, 40 miles away. People felt it 250 miles from the coast. Every firefighter on the dock died instantly. 581 people were killed. Nearly 4,000 were injured. It remains one of the deadliest industrial accidents in American history and one of the largest non-nuclear explosions ever recorded. The same molecule Fritz Haber had pulled from the air to feed a starving continent had just leveled an American port. The nitrogen atom gives life, and when you mishandle it, it takes life back. But Texas City was not the last time ammonium nitrate would detonate in a port. Not even close. In 2013, a battered cargo ship called the Roses limped into the port of Beirut, Lebanon. It was supposed to be passing through. It never left. The Roses was carrying 2,750 tons of ammonium nitrate bound for Mozambique. But the ship was unseaworthy. The owner had abandoned it, and Lebanese authorities impounded the vessel. So they offloaded the ammonium nitrate and stored it in Warehouse 12, right there in the port. Then they just left it there for 6 years. Port officials sent letter after letter to government authorities warning about the danger. At least 6 separate requests to move the material or dispose of it safely, all ignored. The city of Beirut grew up around that warehouse. Apartment buildings, restaurants, nightclubs, 300,000 people living within the blast radius of a bomb they did not know existed. On the 4th of August 2020, a fire broke out in the warehouse. Witnesses saw fireworks igniting nearby, sending sparks toward the nitrate stockpile. At 6:08 p.m., 2,750 tons of ammonium nitrate detonated all at once. The explosion registered 3.3 on the Richter scale. It was felt in Cyprus, 240 kilometers away. More than 200 people were killed. 7,000 were injured. 300,000 were left homeless. $15 billion in damage in a city that was already collapsing. A century after Opao, the story was identical. A neglected pile of ammonium nitrate, ignored warnings, and ordinary people paying the price. The molecule does not change. Only the city does. But the molecule did not stop at explosions. It had a quieter threat waiting. One measured not in seconds, but in decades. Every year, farmers spread roughly 190 million tons of synthetic nitrogen fertilizer across the world's fields. Most of it feeds crops, but a significant portion simply washes away. Rain carries nitrogen off the fields, into streams, into rivers. Across the American Midwest, thousands of tributaries funnel it toward one destination, the Mississippi River. The Mississippi carries all of it south, 2,000 miles of drainage, all flowing into the Gulf of Mexico. And when it arrives, it does not arrive quietly. The nitrogen feeds algae. Massive blooms explode across the surface of the Gulf, thick and green, blocking the sunlight below. Then the algae dies. Bacteria consume the dead algae and devour all the oxygen in the water. Fish flee. Crabs and shrimp cannot flee. They suffocate on the seafloor. Scientists call it a hypoxic zone. Everyone else calls it the dead zone. In 2025, it measured 4,400 square miles, roughly the size of Connecticut. It comes back every summer, predictable as the harvest season that creates it. The farms grow, the dead zone grows with them. And the oceans are not the only victim. Nitrogen seeps into groundwater beneath farms, contaminating drinking wells across the rural Midwest. Nitrates in tap water, in baby formula, in blood. Then there is what escapes into the sky. Microbes in fertilized soil convert nitrogen into nitrous oxide, a greenhouse gas 273 times more potent than carbon dioxide, rising silently from every field on Earth. And still, the fields keep exhaling. Every fertilized acre on Earth leaking invisible gas into a sky that is already too warm. So here is the bargain in full. The molecule that feeds half the world also poisons its rivers, heats its atmosphere, and has detonated inside its cities. There is no clean exit. You cannot simply stop. 4 billion people do not have a backup plan. Fritz Haber understood bargains. He gave his country a way to win a war and feed its people. His country gave him exile and watched gas chambers consume his family. He won the Nobel Prize in 1918. He was chased from Germany in 1933. The same mind, the same chemistry. Two completely opposite verdicts from history. Carl Bosch scaled that chemistry into the largest industrial project the world had ever seen. Then he watched it arm the regime that would become history's worst atrocity. He drank himself to death, not because he failed, because he succeeded, and then had to watch what his success became. The molecule did not choose any of this. Ammonium nitrate has no ideology. It simply does what chemistry allows. Humans made every choice about what that meant. That is the real story this video has been telling. Not the story of a dangerous chemical, the story of what humans do with power they discover before they are wise enough to hold it. It started in a small lab in 1909. A young chemist squeezed nitrogen and hydrogen together under brutal heat and pressure. That was the turning point. Everything after that was a consequence. One reaction: nitrogen plus hydrogen, heat, pressure, catalyst. From that single moment cascaded world wars, green revolutions, explosions, famines prevented, and a warming sky. There is a possible escape route. Researchers today are building electrolyzers powered by solar and wind to make ammonia without burning fossil fuels. Green ammonia, the same molecule, finally made without the carbon cost. We are still making choices about this molecule. The question is whether we will finally make the right ones. If you want to keep following stories like this, subscribe. The next one is just as strange.